Hi everyone, this is Unblur-SLAM, dense neural SLAM for blurry inputs. The key message is that deblurring is not only image enhancement. It changes the geometry that the tracker and the map can trust. Please look at the teaser. The input has motion blur and defocus blur, but the desired output is not just a clean frame. We want a stable trajectory and a coherent dense map. Now look at the problem slide. On the left, a generic deblurring result can look sharper. On the right, SLAM still needs pose, depth, and map evidence to agree. This mismatch is the first pattern. So the question is not only, did the frame become sharper? The real question is whether the deblurred observation preserves the 3D explanation needed by SLAM. Here, focus on the real blur result and the ATE number. The image improves perceptually, but the trajectory error remains high. The pattern is clear: sharper does not automatically mean better tracking. This motivates the method. We treat blur as a geometric nuisance inside the SLAM loop, not as a detached pre-processing artifact. Next, look at the bit video examples. Frame by frame, the result may seem plausible. Across nearby frames, however, the geometry wobbles and local structures deform. That temporal instability is harmful for SLAM. A tracker integrates evidence over many views, so small inconsistencies accumulate into pose drift and bad depth. Now look at the data slide. The four sources are deliberately mixed. The reason is our compound blur assumption: real blur contains optical defocus and motion blur together. At the pixel level, the signal is first spread by defocus, and then accumulated on the camera plane into a motion streak. So training moves from synthetic motion blur to real image motion synthesis, and finally to real defocus blur. On the synthesis slide, look at the exposure window. We interpolate subframe samples, average them in linear color, and use the middle exposure frame as the sharp target. The visual rule is important: the target is not an arbitrary sharp neighbor. It is the center of the same exposure event, so the supervision is physically meaningful. Now look at the physical model. Defocus acts first on the camera plane through a local point spread function. Then camera motion integrates these observations over exposure time. This ordering matters. If we reverse it, the blur model no longer matches the camera optics. So we separate local defocus from global motion integration before feeding SLAM. Here is the refinement policy. Look from left to right. Low blur uses the neural deblurring network. Medium blur adds a PSF cleanup. Severe blur uses subframe defocus and camera plane integration. The pattern is a routing rule. As blur becomes more severe, we add more physical structure, instead of forcing one deblurring operator to handle all cases. Now look at the qualitative ablation. We compare SLAM directly with the full method. The baseline mapping has two source panels. The labels mark input observation and SLAM rendering. This is the evidence SLAM needs. We care about repeated structures, boundaries, and visible surfaces agreeing as the camera moves. On indoor MCD, compare the two runs. The baseline has no added deblurring or refinement. The full method is neural deblur plus multi-view refinement, so the SLAM output is more stable in blurred indoor regions. The trend is simple: the full pipeline is stronger when image restoration and multi-view geometry agree. Finally, look at the trajectory plot. The baseline drifts away from ground truth, while the full method stays close. The RMSE drops from about 0.51 meters to 0.058 meters. The current code has already been released. We will release an improved version of the code base and methodology within 3 months. Thank you.